Hello everyone. Let us now proceed to the next part of our lecture. So we have previously discussed energy balance for closed systems. We will now proceed to the energy balance for open systems. Now for just some notations for open systems, m dot represents mass flow rate while n dot represents molar flow rate. Small letter q will represent the volumetric flow rate while small letter u will represent the average fluid velocity. And you know from your ChemE 101, m dot is equal to the molar mass times the molar flow rate. And from continuity, okay, the volumetric flow rate is simply equal to the cross-sectional area of flow multiplied by the average fluid velocity. Okay, so this is the cross-sectional area. In some references, mas ginagamit ang S, pero for now, let's just use A. And the mass flow rate is equal to the density times the volumetric flow rate, and that is equal to the density times the cross-sectional area times the average fluid velocity. In some cases, you can also represent this as A U over V, where V is the reciprocal of the density. So V again here is the specific volume of your fluid. Okay. Now recall, for an open system, mass can freely go in and out. Unlike a closed system, mass is constant inside the system boundary. So we need to do two balances. One is the mass balance for open systems, followed by the energy balance for open systems. So for the mass balance for open systems, consider a control volume. So the volume that should not change for open system. Okay? Hindi nag-change yung system boundary natin. Thus, for energy balance for open systems, using accumulation is equal to input minus output plus generation or net generation. Wala naman tayong generation of mass, dapat this should be equal to 0. And the rate of accumulation of mass inside the control volume is equal to dm over dt. And everything that goes inside is m dot in. Everything that goes out is m dot out. Now at steady state, there should be no accumulation of mass. So at steady state, dm over dt is equal to 0. So summation of m dot in minus summation of m dot out is equal to 0. Thus, summation of raw AU in is equal to summation of raw AU out. And for single entry, single exit systems, raw AU in is equal to raw AU out, and this is known as our continuity equation. Now for the energy balance for open systems, let's start with the general balance equation. A is equal to in minus out plus generation. Okay, so we know that energy cannot be generated inside, so a generation should be equal to 0. Energy will just flow in and out of our control volume. So these are the terms present in the energy balance for open systems. So we have dmucv over dt. This is the rate of accumulation of energy inside the control volume. Okay. So possible na mag-accumulate yung energy na yan inside this, and this is represented by dmucv over dt, or the rate of change of total internal energy inside the control volume with respect to time. Now, for energy streams going in, we have from syempre, the flowing streams, meron siyang internal energy, meron siyang kinetic energy, and meron siyang potential energy. And same for the streams going out, internal, potential, and kinetic. We also have heat flowing in and out of our system boundary in the form of heat and work. So in this case, shaft work. And we also have, syempre, flow work. Now, one simplification that we can make for energy balance for open systems, you can combine internal energy with PV. Ayan, because H is equal to U plus PV. So pag closed systems, mas convenient si internal energy. But for open systems, combine na natin si PV with U to form enthalpy, which is a much more convenient energy unit. Thus, this will be our energy balance equation for open systems. We can simplify this further, gawin natin delta notation, where delta signifies out minus in. So rearranging dmu cv over dt plus delta m dot h plus u squared over 2gc plus g over gc of the flow streams. So ito magiging parang summation of out minus summation of in lang din, which is equal to q dot plus ws dot. Let us now proceed to some discussion of some examples for open systems energy balance and mass balance with some accumulation inside our control volume. So consider this case. We have an insulated vertical piston cylinder device which contains 10 kilograms of water, 6 kilograms of which is in the vapor phase. The mass of the piston is such that it maintains a constant pressure of 200 kPa inside the cylinder. Now, steam at 0.5 MPa and 350 degrees Celsius is allowed to enter the cylinder from a supply line until the liquid in the cylinder has vaporized. Determine from this the final temperature in the cylinder and B, the mass of steam that has entered. So consider this case for the initial until the final process. Let's say meron dyang piston. Okay? Say may piston dyan that allows it to move to maintain the pressure constant at 200 kPa. So ngayon, how do we proceed from this? Okay, first, let us try to calculate the final temperature in the cylinder. So, ang cylinder natin ngayon, in final conditions, is 200 kPa, tapos no liquid left. Ibig sabihin, enough steam was supplied until all the liquid vaporized. Thus, we now have saturated vapor at 200 kPa. So to find temperature of the steam inside the cylinder, so enough steam was just supplied until all the liquid evaporated. Therefore, all the water inside the piston is saturated vapor at 200 kPa. So we now take a look at the steam table at 200 kPa, and the temperature of saturated steam at 200 kPa is 120.21 degrees Celsius, which is now the final temperature of the steam inside the cylinder. Okay, for our next step, let's proceed to the mass balance. So for our mass balance equation, recall dm over dt, the rate of accumulation of steam inside the cylinder, is equal to m dot in minus m dot out. Now, ito yung cylinder natin. Meron tayong papasok na steam over time. Yan. So based on this, we have no steam going out. Therefore, m dot out should be equal to 0. And m dot in is just the mass of steam going in from our supply line, which is maintained at a constant rate. Thus, our mass balance equation will now be dm over dt is equal to m dot in. And simplifying, dm is equal to m dot in dt. And we can now integrate this. Okay, integrate natin si dm from initial mass inside the initial system, ito yung initial conditions, tapos until the final mass of steam. So ito yung final conditions, ito yung initial conditions. And then we can integrate the time from 0 to t. So integrating mf minus mi, so final mass of steam minus initial mass of steam, this is equal to the mass of steam that went inside the cylinder throughout the whole time period, which is simply equal to the total time, which we don't know, multiplied by the steady mass flow rate of steam going inside the cylinder. And we know from our initial conditions that the initial mass of steam inside the cylinder is at 10 kilograms. Okay, so we have now simplified the mass balance equation for this unsteady state problem. Let us now proceed to the energy balance equation. So for the energy balance equation, again, ito yan. Now, how do we simplify this further? So consider the steam supply again, steam going in, tapos final conditions, ayan, initial, final. We can approximate this scenario such that we can say that, sige, wala masyadong change in kinetic and potential energy. Kasi di naman nag-move yung initial, di naman nag-move yung final. Okay? Tapos, yung flow stream natin ay going in lang. So, nag-assume negligible change in potential and kinetic energy. Now, another thing here is you have an insulated vertical piston cylinder device. So, insulated, we have no heat transfer. Another thing is, wala naman tayo rotating equipment inside the piston cylinder. Thus, shaft work can also be equal to 0. So we have negligible P and KE, since the magnitude of change of P and KE may just be very negligible compared to the magnitude of enthalpy. Usually, yung mga PE, KE na yan, nasa joules lang yung magnitude, whereas yung delta H or enthalpy is in the magnitude of kilojoules or hundreds of kilojoules. Okay? So no heat transfer, no shaft work, and no outlet stream. Therefore, our reduced energy balance equation will now be dmuCv over dt minus m dot in times h in, the specific enthalpy of the steam going inside the cylinder, is equal to 0. And if you rearrange this, dmuCv is equal to m dot in h in dt. And if you integrate this from m initial, u initial, to m final, u final, and then integrate this from time is equal to 0 to time is equal to t, you will get the following expression. So the final mass of steam times the internal energy of the final steam minus the initial mass of steam times the internal energy of the initial steam is equal to the mass flow rate of steam going in times the time times the specific enthalpy of the steam going inside our cylinder. Okay, so meron na tayo ngayong energy balance expression, and we also have our mass balance expression. And we can further simplify this since we don't know the whole time scale of the process. We just know that ang final process natin, tapos na siya when all the liquid water inside the cylinder has been vaporized. So based on our mass balance expression, we can replace this term, the m dot in times t, from the energy balance expression with mf minus mi from our mass balance equation. So combining the two, you will now get mf minus mi is equal to mf minus mi times h in. And in order to solve this, let us have now to read uf, ui, and h in from a steam table. So let us do this. Steam table naman. Okay, so first, UF, the final state is saturated vapor at 200 kPa. So ito na agad si UF. Now, initial conditions natin, you have 10 kilograms of water, 6 kilograms of which is in the vapor phase. So for the initial conditions, okay, for UI, meron tayong quality XI which is equal to 0.6. So we have a 60% quality steam inside the cylinder initially. So meron tayong mixture of saturated liquid water and saturated vapor steam sa loob ng cylinder. So the specific internal energy for the initial state should be between these two, and you can use the linear mixing formula to get the specific internal energy at the start of the process. And lastly, for the enthalpy of the steam going in, we have steam at 0.5 MPa and 350 degrees Celsius. So this is a superheated steam. So we can now interpolate between 300 degrees Celsius and 400 degrees Celsius at 500 kPa. So single interpolation lang naman, thankfully, and you can get H in, which is 3168.5 kilojoules per kilogram. So ayan, so ito na si UF, UI, HN, and MI. And from our combined mass and energy balance expression, okay na si UF, okay na si MI, UI, Mi, and Hn, we can now have a one equation and one unknown, and we can now solve for the final mass of steam inside our piston cylinder device. So solving for the final mass of steam, you can get 22.67 kilograms. Therefore, if you have an initial mass of steam initial mass of steam 10 kilograms, ang final mass of steam natin is 22.67 kilograms. The total mass of steam entered should be the 22.67 minus 10 kilograms, which will give us 12.67 kilograms of steam going in throughout the entire process. Okay, let's now proceed to the next example for unsteady state open systems energy balance. We have a rigid insulated tank that is initially evacuated, which is connected through a valve to supply line that carries steam at 1 MPa and 300 degrees Celsius. So meron tayong steam rigid tank connected to a supply line with a valve. Tapos meron siyang steam going in. So meron siyang m dot steam going in dito. Okay, this is at 300 degrees Celsius and 1 MPa. And then steam is now allowed to go in. Bubuksan yung valve. Okay, this initial steam, Mi, is equal to 0. So initially evacuated. And then, papasok yung steam until, okay, this is now at 1 MPa. Since equal na yung pressure, di na papasok yung steam sa loob ng tank natin. And you can now close the valve once again. So ito yung final conditions natin. So with this, determine the final temperature of steam in the tank. The problem seems so simple. Okay, parang lang. So let's start with the energy balance, the mass balance expression. So using mass balance, dm over dt is equal to summation of m dot in minus summation of m dot out. Now, wala tayong mass going in, wala tayong mass going out, so this is equal to 0. Thus, mass balance, mf is equal to m dot in times T when it's finally integrated, which is equal to the total mass of steam in. Okay, so these are previously derived and mass balance equation. Let's now proceed to the energy balance equation. So for the energy balance equation, we can make the same assumptions. You can have negligible Ke and Pe. You can also have no heat transfer kasi we have an insulated tank, and we also have no shaft work kasi wala naman tayong rotating equipment inside. So our energy balance equation will reduce to d muCV over dt minus m dot in h in kasi wala naman tayong mass going out. So it's equal to 0. And integrating this and rearranging, you will get the following energy balance equation. MFUF is equal to m dot in T times H in. Walang MI kasi wala naman tayong initial mass of steam inside our evacuated tank. Now combining the mass balance and energy balance equation, so m dot in times T is also equal to UF. So we will get MF UF is equal to MF H in. Cancel natin si MF. You will get UF is equal to H in. Meaning, the final internal energy inside the tank is simply equal to the specific enthalpy of the steam going inside the tank. So UF is now equal to H in, which is 3051.6 kilojoules per kilogram. Okay? So H in natin, ito. This is the value of H in. So to get UF, okay, tignan natin ngayon yung internal energy na 300, 400, and 500. So internal energy na 3051.6 is between 400 degrees Celsius and 500 degrees Celsius. At 400 degrees Celsius, it's 2957.9, and at 500 degrees Celsius, it's 3125.0. So you can now perform interpolation to obtain the final temperature of the steam inside the tank, which is 456.07 kilojoules per kilogram. So as you can see, the temperature now of the steam inside the tank is much greater than the temperature of the steam supplying the tank. Okay, why is this? Kasi kanina, yung steam na nag-flow dito sa pipeline supplying the tank is enthalpy, which contains internal energy plus PV, the flow work. So now, pumasok na sa loob ng tank, it's not flowing anymore. The flow work is now converted into internal energy. Kaya tumaas yung temperature sa loob ng tank natin. And that ends the first half of the energy balance for open systems discussion, particularly on steady state energy balance equations. So for the next part, we will now proceed to the steady state energy balance equations.